Hi, everybody. So this is lecture 7, and what we'll be discussing today is conservation of energy. So the big difference between what we were doing yesterday or the last lecture in terms of work kinetic energy is that in conservation of energy, we have a single system where mechanical energy is conserved, and we refer to it, we'll have the two terms. T will be for kinetic energy of the system, and we'll use V for the potential energy of the system, where the V will be both spring energy and gravitational energy. These systems do not involve non-conservative forces, i.e. the applied forces of friction, because they would change the overall amount of energy in the system. An applied force would add energy into the system, and friction would remove energy from the system. But for these systems that can be analyzed using conservation of energy, the total energy of the system, both the kinetic and potential energy, has to remain a constant. However, as we see here with this diagram, we can have a ball at above some distance h above a datum, that the system could be all potential energy and the kinetic energy is 0. Then as we drop the ball, we would end up in a secondary position down here where it's all kinetic energy just before the ball hits the ground, and the potential energy goes to 0. So we'll find that these systems, there's an interplay or a transference between kinetic energy and potential energy. All right, so for the gravitational potential energy, we need to set a datum where we consider the potential energy to be 0. So anything above the datum would have positive gravitational potential energy, and anything lower than the datum would have negative potential energy. As you'll see, most of the problems that we'll work with today, we will locate the condition where the particle or particles of the system would be their lowest point, and we'll typically put the datum there. So it's very rare that in a particular problem we're dealing with negative gravitational potential energy. And the potential energy is just the weight times its height above or with respect to the datum, where W can be either a positive or a negative value. For the spring potential energy, it is just the amount of energy that is stored within a spring at any given time. So this quantity S that we will square is just the amount that the spring is changed from the unstretched position, or the neutral length of the spring. So in this case, we have a positive stretch of the spring for a distance s, and the amount of potential energy is 1/2 ks squared. If we compress the spring, we still have the same amount of stored potential energy, 1/2 ks squared. It's always a positive quantity. All right, well, let's look at an example problem here. We have a collar A that has a mass of 15 kilograms, and we have a mass B that has a mass of 25 kilograms. Mass A is attached to a horizontal rod, and it's frictionless. It's allowed to move smoothly along the rod, and it's attached to a spring with a spring constant of 850 Newton meters. And what we're asked for is to determine the velocity of mass B when it has moved downward 0 meters from its present position. So B is going to move down. We can call this the datum. So when mass B gets down to the bottom, it will have 0 gravitational energy. And since B and A are attached by a string, as B moves down 0.4 meters, mass A will move to the right 0.4 meters. And at the instant shown, the spring is unstretched. So we will be able to figure out, using Pythagorean's theorem, the current length of the spring, and then A will move to the right, so this 0.45 will become 0.85. So there's no non-conservative forces, there's no friction, there's no applied forces, so we can apply the conservation of kinetic energy, of conservation of mechanical energy. All right, so the kinetic energy. Masses A and B are connected such that the velocity A will equal the velocity of B. We are told at the instant shown, mass B is moving downward at 2.25 meters per second. So the kinetic energy will be 1/2 MAVA squared plus 1/2 MBVB squared. A and B, the velocities of A and B are equal to each other. We set that equal to 2.25 meters per second. And we find out that the total kinetic energy of the system is 1/2 2.25 squared plus the sum of its masses for a total kinetic energy of 101.25 joules. The potential energy of the system will be both gravitational and spring energy. So only mass B changes in height, so we'll set the datum at its final height. So the gravitational potential energy of the system is the mass of B times G times its height above the datum, which is 0.4, for a total gravitational potential energy of 98.1 joules. At the instant shown, which we'll call configuration 1, the spring is at its unstretched length of, so we'll call that L1 is equal to LO, and the unstretched length of the spring using Pythagorean's theorem is 0.15 squared plus 0.45 squared, taking the square root, so a total length of 0.4743 meters. But since they're equal to each other, the potential spring energy is 0. So for a total amount of energy in the system at configuration 1, we have kinetic energy, we have gravitational potential energy, and our spring potential energy is 0. So we have a total amount of energy in the system of 199.35 joules. All right, so now we're going to look at configuration 2. So at configuration 2, we'll have both masses, mass A and mass B, will both be moving at the same velocity, which we will call velocity 2. The gravitational potential energy is going to equal 0 because mass B will have reached its lowest point. And the spring, for the spring potential energy, we will have to move the mass A here to the right 4 meters. So we get a length, this height doesn't change, 0.15, but so 0.15 squared plus the 0.45 plus the additional 0.4 squared gives me a length of the spring when we're at configuration 2 of 0.8631 meters. Plugging that into our spring potential energy, 1/2 the spring energy is 800, the spring constant is 850 newtons per meter, and this is the new length of the spring, this is the original length of the spring. That gives me a total distance S, which we square for a total spring potential energy of 64.24 joules. Adding those together, we have the kinetic energy, which we don't know what the velocity 2 is. That's what we're looking for. 0 gravitational energy and plus 64.24 joules of spring energy. So now applying conservation of energy, we set the total energy of the system at configuration 1 equal to the total energy at configuration 2. The only unknown is V2, which will be the velocities of both A and B. So solving this, bringing the 64.24 over to the right-hand side, dividing through by 20 and taking the square root, we end up with a total velocity, or final velocity rather, of 2.6 meters per second. All right, so that's the basic premise for how we're going to go about applying these problems. Let's look at one. Okay, this second example problem, we have a toy gun that has a spring attached to it and a ball up against the spring. So we're told that the unstretched length of the spring is 100 millimeters. The spring is then compressed and locked in the position shown, which is 50 millimeters. When the trigger is pulled, the spring unstretches, but only an additional 12.5 millimeters. So it doesn't go all the way back to its unstretched length of 100 millimeters. And the 20-gram ball moves along the barrel. Determine the speed of the ball when it leaves the gun. So now the ball is not changing its height, so we don't have to deal with gravitational potential energy. It's all going to be spring potential energy. So we have the spring, which is with its unstretched length of 100 millimeters, and then we compress it 50 millimeters. So this will be configuration 1. So the initial energy in the spring is 1/2 ks squared. That should be a squared, equals 1/2 times 2,000. The spring constant is 2 kilonewtons per meter, so 2,000 newtons per meter times its length, which is 50 millimeters, so that which is 0.05 meters squared, for total energy contained in the spring of 2.5 joules. Then the spring is allowed to stretch 12.5 millimeters for a total compression of 37.5 millimeters, or as we're going to write it here in meters, 0.0375. So 1/2 times 2,000 times the new compression of the spring of 0.0375 for a total amount of energy of 1.4006 joules. For the kinetic energy, in configuration 1, the speed is 0, so there's no kinetic energy. In configuration 2, it'll be moving at its velocity, which is what we're looking for, v2. So we have the initial spring energy of 2.5 joules and the initial kinetic energy is 0. The final spring energy of 1.406 joules and the new kinetic energy. So equating the configuration 1 with configuration 2, we'll get rid of the ones that are 0, the initial kinetic energy, and the 2 gravitational kinetic potential energies, because they don't change. We end up with 2.5 joules equals 1/2. Now the weight of the ball, or the mass of the ball, is 20 grams. That's 0.02 kilograms times v2 squared plus 1.406 joules. Solving for the final velocity, we get that the ball exits the gun with a speed of 10.5 meters per second. All right, the next example problem is one that we've looked at. We looked at it last lecture, solving it using work kinetic energy theorem. But what we're going to do now is we recognize that there's no external forces, there's no friction, so we can solve this using just conservation of mechanical energy. So we start out by equating the initial energy of the system with the final energy of the system. We're going to set the datum for this problem where the sphere is at its 0 position, so where theta equals 90 degrees, and we're going to look at the initial kinetic energy of the system is equal to 0 because it's released from rest. The initial potential energy of the system will have both gravitational and spring energy, where it's mgh1, where h1 is going to be 0.45 meters, the distance above the datum, and we need to have 1/2 KSI squared. So the height will be 0.45 is what we're saying, and SI will have to be the initial stretch of the spring minus the equilibrium length of the spring, which we need to determine. So we determine the equilibrium, the initial length of the spring here. When it's at a zero position, the two legs of the spring are 0.4 and 0.3. So the initial length of the spring is the square root of 0.4 squared plus 0.3 squared, or 0.5 meters. The equilibrium, the amount the spring is stretched at that position, is going to be calculated from the knowledge that the spring has a tension of 150 newtons. So the force in the spring is 150 newtons, the spring constant is 500 newtons, and this is the amount the spring is stretched already, which is 0.5 minus the equilibrium length. So we do 150 divided by 500, substituting in for 0.5, and 150 over 500 is equal to 0.3. So solving for the equilibrium length, we get 0.5 minus the 0.3, gives us an initial an equilibrium length of the spring of being 0.2. So the total potential energy of the system will be the gravitational portion, 15 kilograms for the sphere, times the acceleration of gravity of 9.81 meters per second squared, times the height above the datum of 0.45 meters, and then the kinetic energy of the spring, 1/2 times 500 the spring constant, and the initial, the starting length of the spring is 0.5 minus the equilibrium length of the spring is 0.2, so the stretch of the spring is 0.3 meters squared. That gives me a total potential energy of 88.65 joules. All right, so that is the initial kinetic energy is 0, initial gravitational and spring potential energy is 88.65. So now the final configuration will be 1/2 mv final squared, and then we have the potential energy, gravitational potential energy. The height will be 0 because the mass will be at the datum, so this term goes to 0, and our stretch of the spring will be 0.4 plus 0.3, so 0.7 meters will be the length, the final length of the spring, minus the equilibrium length of the spring, so 0.5. So the total final potential energy is 0 for gravitational, plus 1/2 times 500 times 0.5 squared, which gives me 62.5 joules. So initial kinetic energy 0, initial potential energy 88.65 will equal my final potential energy, which has my unknown, this final speed of the sphere, plus the final potential energy of 62.5 joules. Solving that, we get a final kinetic energy, or final velocity rather, of 1.87 meters per second. And you can go back to the work we did in last lecture and verify that those two values are identical to each other. So now we'll take a look at some example problems. All right. So our first example problem, we have a 2-pound block which is attached to a spring, and it's given an initial velocity of 20 feet per second downward. We're told that the spring has an unstretched length of 2 feet, so it is unstretched when it's in its initial position, and we have the spring stiffness of 100 pounds per foot. It wants us to determine the velocity when the block is at a position here, C, where S equals 1 foot. All right, so let's take a look at what we have here. So we have a situation where we know what the final position of the block is going to be, or the collar, at point C. And when we do that, the length of the spring will be, using Pythagorean's theorem, the square root of 5 feet. We're told stuff about the initial condition, so that we have the velocity is 20 feet per second. The weight is going to be 2 pounds, but we need the mass. So the mass is going to be 2 pounds divided by the acceleration of gravity. In the English system, this is 32.2 feet per second. We're told the spring constant is 100 pounds per foot, and we know the initial length of the spring is 2 feet. The last bit of information here would be to choose the datum, and we'll set the datum here at 0 feet. Okay, so let's say we're going to apply the conservation of energy. So that would say that the kinetic energy at point A plus the potential energy at point A has to equal the kinetic energy at point C plus the potential energy at point C, not B. Okay, so at the value for TA is going to be 1/2 mVA squared, which will be 1/2. The weight, the mass is 2 over 32.2, and the velocity is 20. And we'll square that, and we will work out the values, and that is 12.42 pound-feet. Okay, and we have only, the potential energy is only going to be gravitational potential energy. We can write them both down, but we know that the initial stretch of the spring is the unstretched length of the spring is 2 feet. So the only thing we have is it's the fact that it's 1 foot above the datum. So we will write mgh, and we get the mass is 2 over 32.2 times g, 32.2. So we could have just used the weight, and the height is 1 foot. So we end up with 2 pounds, 2 pound-feet. Okay, at the location C, at TC, we don't know the velocity. That's what we're looking for. So it's 1/2 mvc squared. And the potential energy will just be spring potential energy because it's going to be at the datum. So VC will just be 1/2 K SC squared. So 1/2, K will be 100 pounds per foot, and SC is going to be the square root of 5. That's the length minus the unstretched length, which will be 2, and that is going to be squared. And that works out to being 2.786 pounds per foot. Okay, so we just need to write out the conservation equation here. So TA will be 12.42 plus VA, which is 2, and this is going to equal 1/2. Now the mass will be 2 over 32.2. Times VC squared plus VC. well, VC velocity and VC being the potential energy. So sometimes we have problems with the alphabet here, but this is 2.786. So writing out our final piece here, we will be 12.42 plus 2 minus 2.786. We can cancel out these two 2's, and then we'll multiply that by 32.2, and we'll take the square root of the whole thing, and that gives us VC. So the velocity, this works out to being VC equals 19. It's 19.36, but I'll write it as 19.4 feet per second. So that gives us our answer. So again, recapping, you take a look at all the conditions at A, knowing its initial kinetic energy and its height above the datum, and also how much spring energy is there. So there was gravitational potential energy, but no spring potential energy. And then when we get to point C, we have kinetic energy, no potential energy because it's passing through the datum at that point, but there was spring energy. All right, let's look at the second problem. Here we have a spring that we're told is 750 millimeters long, and it's compressed and confined by plate P, which can slide freely along vertical 600 millimeter rods. So basically what we have here is a spring that is compressed by 150 millimeters. There's a 40 kilogram block. It's moving downward at 5 meters per second when we see it, and it is 2 meters above the plate. We want to determine how far the plate moves downwards when the block momentarily stops after striking it. Because, of course, once it stops, the springs will release and it'll bounce back up. So we're basically stopping time. All right, so let's see what we have here. So I'm in my diagram here, I'm noting that what the problem is essentially looking for. It's looking for this quantity D. The block's going to fall down through 2 meters, and it's going to hit the plate, and the plate is going to compress an amount D. But let's take a look at these three diagrams here. So this is what this spring would look like in its unstretched state. We're looking at it right now where it's been compressed 0.15, and here's 0.6. And what we're looking for is this situation where the spring will be compressed 0.15 plus D. So when we're looking for the final amount of energy stored in the spring, it's going to be 0.15 times D. Our other bits of information here, the mass of the block is 40 kilograms, and the spring constant was given to us as 25, it's written here, 25 kilonewtons per meter. So a kilonewton is 1,000 newtons, so 25,000 newtons per meter. The initial velocity is 5 meters per second, and the height above the datum is 2 plus D. The final velocity that we're interested in is 0, and the height above the datum will also be 0. All right, so now what we need to do is essentially write out our initial kinetic energy and potential energy. So let's write that out here. We'll say T plus V, I'm going to combine them together, and I'll just say, here's my initial condition. So it's going to be 1/2 times mv squared. The mass is 40 kilograms. The speed is 5 meters per second. So 1/2 40 times 5 squared. Now, plus, we know it's height above the datum, so it's going to be mgh. So 40 times 9.81. The height above the datum is 2 plus d. And now we also have to account for the fact that the spring itself is compressed 0.15. So the total energy in the spring is 1/2. K is 25,000. And it's 0.15 squared. Now, if we work all those numbers out, we can combine our values and we'll end up with a value of 1566.05 plus 392.4 D. All right, now we're going to look at what the final condition will be. So T plus V final, there's no kinetic energy. All right, so this term was kinetic energy. It's not going to have any of that. There's no height above the datum, so the only thing that it has is going to be spring energy, and that will be 1/2 times the spring constant, so 25,000, times 15.15 plus d. And this term gets squared. So if I write this thing out, it'll be, evaluate that binomial, and we're going to end up with a quadratic. So it's going to be equal to, you can double check my work, 281.25 plus 3,750D plus 12500 D squared. All right, so this is my initial energy in the system, and this is my final energy in the system. So what we'll need to do is equate these two, collect all our terms. It's going to be a quadratic equation, which we'll need to solve, and we'll take the positive root. Typically in a situation like this, in this type of situation, you'll usually get a positive and a negative root, and it's the positive root is the one that's going to be the one that you will end up using. So we will write this out. So let me just change colors here. So it's going to be 1566.05 plus 392.4, and this is going to equal 281.25 plus 3750D plus 12500 D squared. Combining my terms and making it into a quadratic equation, we'll end up with 12500 D squared plus 3357.6 D minus 1284.8 equals 0. So this is what we need to solve. So we'll solve that quadratic equation. I'm going to let you double check my work for you. I don't think you want to watch me solving a quadratic equation right now, but we end up with our answers Since it's a quadratic, we end up with two answers. So we get 0.213 meters, and D equals negative 0.482 meters. The negative doesn't have any physical sense, so the first value is what we're looking for, and we end up with a result of D equals 213 millimeters. We can report it back as millimeters since that was the initial unit that was provided to us in the problem. Everything was given in millimeters. So we end up with a value of 213 millimeters. Okay, now the next thing we're going to do is we're going to look at a topic now we're in particle kinetics, and we're introducing impulse and momentum. So where we essentially start with is we start with Newton's second law. So force equals mass times acceleration. We can write the acceleration as the time derivative of velocity. So, and then I can rewrite this, bringing dt over to the left-hand side. So I can say f dt equals m dv. And a lot of times what we do is we assume the mass doesn't change, so we can take the derivative, just the differential of the term mv. If I integrate both sides, just integrating dmv, I'm just going to get mv back. But on the left-hand side, I don't know how the force term will vary as a function of time. So I'm left on the left-hand side with the integral between points time t1 and t2 of f dt. And on the right-hand side, I just have the change in momentum. Mass times the velocity at time 2 minus mass times the velocity at time 1. We note that this is a vector equation, and what we're going to call these terms, the left-hand side is referred to as impulse. Force applied over a set amount of time will cause a change in linear momentum. Because these are particles, we don't deal with the extent of the body, so we only have to look at linear momentum. Since it's a vector equation, we need to look at all, if it were in 3 dimensions, we would have fx, fy, and fz, and vx, vy, and vz. Typically for the problems we'll be looking at, will typically only be in the 2-dimensional realm. But you have to take into account that these are vector equations. So we'll be looking at that in the example problems that we take a look at now. All right, so we have this minivan here, and it says for a short period of time, the frictional driving force acting on the wheels, unusual units here in the SI, a 2.5 megagram van is FD equals 600 t squared newtons, where t is in seconds. So if the van has a speed of 20 kilometers per hour when t equals 0, determine its speed when t equals 5 seconds. So we're essentially looking for an impulse that's occurring over a period of 5 seconds, and this is a time-varying force. So let's take a look at units here first. 2.5 megagrams, 1,000 kilograms is 1 megagram, so the total mass of the vehicle is 2,500 kilograms. We're given the units in kilometers per hour, but we typically work in meters per second. So 1 kilometer is 1,000 meters, and 1 hour is 3,600 seconds. Working out the values, we have 5.556 meters per second. Okay, so the motion and the force all act in the positive x direction, so we only have a single equation to work with. So we'll say the initial impulse the initial momentum plus the impulse that's applied to it between times t1 and t2 will equal the new momentum of the object. So the impulse is between 0 and 5 seconds. The force is a time-varying force of 600 t squared dt. And evaluating the integral, we can take the 600 out. T squared becomes 1/3 t cubed. Evaluating between 5 and 0 is 600 divided by 3 is 200. 5 cubed, it works out to being 25,000 Newton seconds. Those are the units of linear momentum. The initial momentum is 25,000 kilograms times 5.556 meters per second. So we need to make sure that these two units are the same. So what I want to do here is multiply this by seconds over seconds. So this equals a kilogram meter per second squared times seconds, which gives me newtons times seconds. So when you're sometimes evaluating the FDT, you're going to end up with Newton times seconds, whereas when you're evaluating your linear momentum, you'll end up with kilogram meters per second. So, but you want to verify that they are the same. All right then, so we have 13,890 plus 25,000 is going to equal the linear momentum at time 2. So the mass is 2,500 times Vx2. Solving for our values, we end up with Vx2 being 15.6 meters per second. So that's 13,890 plus 25,000, all of that divided by 2,500, and then just converting ourselves back to kilometers per hour to report our answer in the same units we were given. But if you left it as 15.6 meters per second, that would be fine. Or we can report our answer as 56.2 kilometers per hour. And all I'm doing down here is doing what I did up here, verifying my units. Okay, second problem. A tank car has a mass of 20 megagrams and is freely rolling to the right with a speed of 0.75 meters per second. So we're given the initial momentum. If it strikes the barrier, determine the horizontal impulse needed to stop the car. So we have an initial momentum. We know there's going to be an impulse. The final momentum is going to be 0. And it says, stop the car if the spring in the bumper B has a stiffness, K goes to infinity, the bumper is rigid, and B, K equals 15 kilonewtons per meter. So they're putting a little wrinkle in here on us. So what we should recognize is that this is a trick question because the design of the spring doesn't matter, right? We essentially have an initial momentum, the mass, 20 times 10 to the 3 kilograms times its initial velocity. Then there's going to be some impulse applied to it, which is going to bring the momentum to 0. So essentially the impulse is the opposite of the incoming momentum. So I bring this to the other side, minus 20 times 10 to the 3 times 0.75 meters per second equals minus 15,000 kilogram meters per second. The impulse is negative because the overall momentum is decreased, right? These are vector equations, and the impulse can have either a positive, if it has a positive value, momentum will increase. If the impulse is negative, the overall momentum will decrease. Okay, Let's look at two example problems. So our first example problem, we have that a 0.5 kilogram ball strikes the rough ground and rebounds with velocities shown. So we have an incoming velocity vector that's at 45 degrees to the horizontal at 25 meters per second. The ball rebounds at 10 meters per second at an angle of 30 degrees. So assume that the ball does not slip when it strikes the ground and neglect the size of the ball and the impulse produced by the weight of the ball. So we're just looking at, all we're looking at is the initial momentum and the final momentum, and we're looking for what is the amount of the impulse. Okay? So let's take a look at how we are going to approach this problem. So what we'll do is, and we're going to recognize that we have vector equations here. So we will say my initial momentum, m times v1, will equal 0.5 kilograms. That's the mass of the ball. And we need to impose our xy coordinate system on. So we'll say 25 cosine 45 degrees I minus 25 sine 45 degrees J. That's my initial momentum. The final momentum would be mv2. The mass stays the same. And in this case, the velocity vector would be 10 cosine 30 degrees I. And now we're going in the positive y direction, so we have plus 10 times the sine of 30 degrees J. Now we write out our momentum equation, mv1 plus the integral between t1 and t2 of f dt, where f is a vector, equals mv2. Now we look back at the problem statement and we're not given any information about time here. So we don't know how long it's been in contact with the ground. So essentially what we're looking for, it says determine the magnitude of the impulse. So we're just calculating this term here. So what we'll be calculating is the integral of f dt between some time 1, t1, and t2 will equal mv2 minus mv1. So this will equal, I'm going to take my 0.5 out, and we'll say the I component of v2 will be 10 cosine 30 degrees minus 25 cosine 45 degrees. So that's going to be my I component plus the J component, 10 sine 30 degrees minus, it's going to be minus a minus, so we will get plus 25 sine 45 degrees, and that's my J term. So evaluating both of these, we end up with, this will be equal to 0.5 times negative 9.017 I plus 22.68 J. And evaluating, multiplying through by 0.5, we end up with 4.509 I plus 11.34 J. And my units are kilogram meters per second. The problem statement itself is looking for the magnitude of the impulse. So we're finding out the magnitude. So it would be the absolute value of the integral of f dt. And this will equal the square root of 4.509 squared plus 11.34 squared, which gives me a final answer of 12.2 kilograms meters per second. So that becomes my final answer. So a lot of times in the problems like this, we don't actually have to evaluate the integral. We're just looking at the change in the momentum of the problem itself. Okay, next problem. We're in the English system. We have a 0.1 pound golf ball is struck by the club, then travels along the trajectory shown. So this is going to be a projectile motion problem partially. Determine the average impulsive force the club imparts on the ball if the club maintains contact with the ball for 0.5 milliseconds. So we do have some information here. We're going to be able to calculate the force given to us. All right. So for the mass, we're in the English system, so it's going to be 0.1 pounds divided by 32.2 feet per second. We're told that the delta T is half a millisecond. So half a millisecond, converting that to seconds, it's 0.0005 seconds. Now, what we have over here is a situation where the initial momentum of the particle is zero, right? Before the ball is struck, mv1 is equal to zero because it has no velocity. Then the ball is struck by a force and it leaves in the exact same direction. So we're going to find out that the force, the impulse, and the velocity 2 vector are in line with each other. So we can write out our equation as this. We can have m v1 plus the integral of f dt is going to equal m v2, where this term is zero, and we can approximate the impulse by being F times delta T. So we're not going to look at how the force varies through that interval. We're just going to assume it's a constant force being applied over a set amount of time. And since it's a vector equation, but if we look at our two green arrows, they're in the same line with each other. So this essentially works out to being a single linear equation. So we're going to say that F delta T is going to equal M times V2. And we know what delta T is. So F, that's what we're looking for. The average impulsive force is going to equal M V2 over delta T. We know the mass, we know delta T, so the rest of this problem turns into a projectile motion problem. So we need to go back and dust off our projectile motion abilities here. So let's do that. So we know the distance the ball travels. So distance, and we know that it's going to be the horizontal component of the velocity. So it's going to be V2 times the cosine of 30 degrees times some value t is going to equal 500 feet. So we get an expression for t, the time of flight, as being 500 divided by V2 times the cosine of 30 degrees. Now, we also know that the Vy as a function of time is equal to minus gt plus Vy naught, right? That is one of our standard equations. So we know our initial velocity, we know the final velocities. So we can write this as minus, so when the ball lands, right, it has, when the ball takes off, it has a positive velocity equal to V2 sine 30 degrees. And when the ball lands, it's equal to V2 times the sine of 30 degrees. What goes up must come down. So it takes off with a certain upward velocity. When it hits the ground, it has the same velocity, but they're in opposite directions. So what we get over here is this is the final velocity over here. So minus V2 sine 30 degrees equals minus gt plus the initial velocity, which is V2 times the sine of 30 degrees. Now again, solving this for t, if I bring this term over to the left-hand side and this term over to the right-hand side, you'll see that we'll be adding V2 sine 30 degrees to both sides. So we'll end up with a value of, for t, being equal to 2 times V2 sine 30 degrees divided by g. So now I have two expressions for t, one from the horizontal component of my motion and one from our vertical component. I can combine these two or set them equal to each other. Everything's known except for V2, and we can go ahead and solve. So we'll do that here. So 500 over V2 cosine 30 degrees equals 2 times V2 sine 30 degrees divided by g, which will be 32.2. This then gives me V2 squared will equal 500 times 32.2 divided by 2 cosine 30 degrees times the sine of 30 degrees. And solving for V2 then, we get that, taking the square root of that, we get that V2 is equal to 136.3 feet per second. Now going back to my original problem, now that I've solved the projectile motion problem, we can find out our final value is F equals the mass, so 0.1 over 32.2 times V2, which is 136.3, divided through by delta T, which was 0.0005, for a total impulse of 847 pounds. Okay, so kind of a fun problem, not that much in dealing with the momentum, impulse and momentum, pretty straightforward. The challenge of this one was going back and making sure you remember how to do projectile motion. Okay, so that's all we have for this lecture. I will see you